All right, so thanks for this opportunity to give a talk on this seminar, and thanks for coming to listen. And want to thank the organizers for organizing this this semester here at the Newton Institute. It has been great so far, and it's been a great experience. So I'm really thankful that I can hang out here. Okay, so I will talk about polynomial maps, Witt factors, and Real THH. So all of these, what I will talk about, is joined with Emmanuel and Dotto in Bonn and Christian Moy in Stockholm. Right, so let me start with the very elementary algebra. So when we go from characteristic equal to p to characteristic equal to 0, so go from one to the other. So there are some phenomena happening, and one of the easiest things you can observe is the following thing. So you can take, say, prime is equal to 5, and you can take f5 and consider two maps between f5 itself, not that many maps, and this time I just want to consider it as a set with the multiplication, so then I can consider a square and I can consider cube. These are not ring homomorphisms, but at least they are multiplicative maps, and if you compose them, it's not hard to check, but it's the same as square again. It's actually to the sixth, but to the sixth over f5 is the same as square. And now you can think about what's the corresponding statement in characteristic 0, and you can try to look at it. So when I think about characteristic 0 corresponding object to f5, I think about 5Alex. So let me just do something like this. And so then the same kind of thing doesn't hold anymore, for obvious reasons. Compose these two, and this is definitely not square again. But on the other hand, if you do something slightly different, namely you take now instead of cube, you just take square in both places. And this is just equal to the fourth map. Same kind of thing also holds over 5Alex. So I'm making here some trivial observations. And you will ask me, why are you doing this? And so the reason is that I want to give you a conceptual explanation why this is happening and here this is happening. Again, you will tell me there is a very simple reason for that, because 2 times 3 here is bigger than 5, whereas here 2 times 2 is less than 5. So this is why this is happening. But yeah, you see. But soon we will see that actually this thing, what we see here, is a very maybe special case of some kind of procedure going from characteristic P to characteristic 0 behaving with respect to certain compositions of certain kind of maps. And so I want to give you some kind of conceptual picture which will explain morally like why these kind of things should happen when you pass from characteristic P to characteristic 0. And so passage from characteristic P to characteristic 0 is often done by taking P-typical defectors. That's a general procedure which does this. So let me say a few words about what this construction is. I mean, most of you definitely have seen it and used it. So I'll take m any natural number, possibly infinity. And so I want to consider an A any ring. Is any ring. Commutative. Any ring is commutative in this document. Just write it once. And so then you can define a functor Wm going from commutative rings to commutative rings. So including m is equal to infinity case. So there is a unique factor, Wm, such that following two things hold. The first one is that if you take a ring R as a set, so Wm R as a set is always equal to a product of copies of R from 0 to m, so including the infinity case. And the other property is that the specific map called the ghost coordinates or ghost map W from Wmr into product of 0 to m copies of R, which maybe I should write the first three coordinates and then you'll see the pattern. So W0 of some kind of vector like this is just R0, and then W1 is R0 to the P plus P times R1, and maybe W2 is R0 to the P squared plus P times R1 to the P plus P squared. And then this keep continues like that. So the two conditions as a set, this is just a product, and the ghost map is a natural ring homomorphism. So it's a natural transformation of ring valued functors. And if you put these two conditions, then there is a unique ring structure that makes this into a commutative ring. So just to see right away examples how this is related to the things what we were talking about, we should look at elementary examples of this thing. So this notation will always stand for the infinity, and usually this is how traditionally in literature this thing is denoted. So you can take the Witt vectors of Fp for any prime p, and that's just so right. I said p-typical once, and everything what I will talk about today will be p-typical. You can take p-typical Witt vectors of Fp, and then just add numbers. If you want even more examples, you can take Fpn, and then this is just doing zeta Pn minus 1. So we know that by Hesselholt lemma, zeta P minus 1 is here, so this fits with this first isomorphism. So no fancy example why we should care about Witt vectors is you can take a QP, you can take its algebraic closure and complete this with respect to the topology. And so from there you get actually something called CP, and then you can take ring of integers of this OCP. And so a very common thing to do in number theory these days is to consider this ring, Witt vectors of OCP, which is denoted by a inf, sometimes also called as Fontaine's period ring, a inf. And so this thing plays a central role. In the Hodge theory. So it's very interesting object for number theories. So what about topology? So topology. So now I slowly start motivating why am I interested in Witt vectors. So the first thing I want to mention, there is a theorem by Hesselholt and Madsen. This theorem is way more general, but I'm just going to state the version which I need. So for any commutative ring, okay, you can consider THH of A. And so now I didn't assume in this audience that people need Witt vectors, but I'm of course going to assume you know what is THH. So you can take its CPN fixed points, and you can consider its phi 0. And it turns out that this is isomorphic too, and now I shouldn't make a mistake with the number. It's Wn plus 1 of A. So it's n plus 1 truncated typical Witt vectors on A. And so this is the beginning of all the connections between THH and related things with arithmetic, which has been used in these days a lot. But this was one of the first theorems showing that these kind of connections are happening.
We show you a number in this, right? You know, for n equals 0, the left hand side is A, but W1 has 2 copies of A.
So when n is equal to 0, then this is no fixed points, so it's by 0 of THH. Which is A, and then I'm also taking W1 of A, which is
2 copies. You have a product from 0 to
okay, that was wrong. So I should have had product there from 1 to A, of course. But then I still will be using W0. So that's a bit of an awkward notation, but people do this.
R0 is the first coordinate that's there, or is R0 not there?
0 to n minus 1 is actually the right word. Okay, great. Yeah, thanks. That's so infinity minus 1 is of course infinity. Okay, yeah. So that's a good point. All right. So are we happy with this? Or? Yeah. So then it fits better with W0. But of course, in literature there are many different combinations of numbers. You start from 1 to 0. Okay. Good. So this is the theorem, and so now how do I end up with this vectors? So we've been working on, Christian, Emanuele, and also some other people have been working on the real topological homology. And let me give you just a very quick introduction into this. And so then some kind of Witt vectors also show up in that case, and then eventually you arrive to things like polynomial maps, which I will motivate. So before that, just, yeah?
There should be 5 consonants in a row.
Real topological Hoch,
Have to correct your German, right?
yeah. Yeah, that's correct. Good. Sorry. Okay, so just to remind you how you define ordinary THH or also HH. So tensor always means tensor over sphere. So you take, for example, cyclic bar construction, and there's certain maps here that you have, which I don't want to recall, and then you take its geometric realization, and this is the HH of A. So now, actually there is, so now we can start with A ring, so commutative ring. So everything is commutative, of course you can do all of these things without any commutativity assumption. So A is a commutative ring with involution. Let's take something like complex notation. So then, on the cyclic bar construction of A, you can define a ZMO2 action everywhere. So here you have an obvious ZMO2 action. And so all the places, and so just in formulas to give you an intuition what this is. So let's call this, I don't know, tau, the generator of ZMO2. So involution of A0 tensor A1, so on again, is just A0 bar tensor A bar and so on, A1 bar. So on the picture, what does this really do? So you should think of THH as some kind of configurations on a circle. Any question?
Is that what you meant? 0, n, and then it goes?
Yeah. I leave A0 there. Can show you the picture. So that maybe it's the order of 2. Sorry?
Didn't you say tau is an evolution?
Yes.
Okay, yeah, it goes.
It is an evolution. So, I mean, I guess if I show you the picture, then you're gonna be completely convinced that it's the right thing to do. So, you have, like, morally speaking, THH is some kind of configurations like that. And so now what I'm just telling you, this operation is, of course, putting bars on all of these elements, but it just also flips the circle. And basically, this construction morally is choosing some preferred coordinate axis, which is an x-axis in this case. And I put A0 here. And so this A0 stays there where it is, but everything else is flipped. So this is where this formula comes from.
So you could put another choose another convention?
Yes,
or it does
you
not?
can do that. Both resulting things will be isomorphic. And somehow for the computations I will be talking about today, this doesn't matter. But there is also a way of defining this thing without choosing any axis if you do something like factorization homology or something like that. I think this way of defining it is more sort of straightforward.
So does this correspond on realization to the flip of S1?
Yes, definitely.
Flip
Yeah.
plus
Yeah.
involution.
Right, it's basically S11 and sort of acting, so SSC. Right, so altogether what we get, this is not a Zemo 2 equivariant simplicial object, but it's a real simplicial object with two action. If you take geometric realization, then what you get is the real THH of A, which I want to denote by THR of A.
Does this have to be about commutative rings?
No, definitely not. So if you start with an anti-involution,
Right.
then you can do the same thing. So I said everything, what I'm saying, a lot of things work for any ring with anti-involution. But of course today I will not just do an rings. Okay, so here is the first thing and I have to mention here some names. Of course, this was first defined by Hesselholt and Madsen. And they have some slightly different construction using Bochster's model, but eventually we managed to see that you can also do it using bar construction. And so also Hesselholt in her thesis, and also Emanuele Dotto in his 2012 thesis, they all studied this structure, and also they studied the corresponding O2 action you get on this real THH. So the THH has S1 action, but now with this action of the flip of S1, we altogether get actually O2 action, and somehow this choice of coordinate basically corresponds to identifying O2 with the semi-direct product of S1 and Zemo 2 if you want. But again, this doesn't have to be the case. You can also do it without one. Okay, so now one of the first results, what you have on this real THH is to compute the group of components of this thing. So I don't want to go into too much motivation of this object, because eventually I want to go to algebra. But of course there is things like Hermitian K theory, which we heard about a couple of weeks ago here. And these kind of constructions of the real versions of THH are motivated, of course, by studying real algebraic K theory and Hermitian K theory. There are all these real refinements of trace maps and so on, which I don't want to discuss. Okay, so now one of the first things which we showed 2 or 3 years ago, in a joint work with Emanuele, Christian, myself, and Sunele, and also some earlier computations which were not quite this, but some kind of quotient of this was done by Hesselholt in her thesis. Is that if you take the Zemo 2, and so now Zemo 2 is exactly this flip, so I have one chosen Zemo 2 inside this construction, even though it doesn't really matter. If you take Zemo 2 equivariant pi 0 of this thing, this is isomorphic to as a product like that, where these are the fixed points of the involution with the equivalence relation, which I just want to write here out. So it does allow you to put additive and multiplicative transfers at different sides of the tensor product. Go to C, and C bar, and B. So this is what we showed. So this thing is not just a group, it is also a Mecke functor. Even more, if you take a commutative ring, it's actually a Tambara functor. It has additive as well as multiplicative transfers. But just let me describe for you the multiplicative transfer, which I'm mostly interested in this talk. So this is A, we know that, and so there is this multiplicative norm going from here to pi 0 of THR. And so if you look at this calculation, what we did, and if you know this, so let me just from now on write out that this is a quotient what this norm really does is that it just takes a copy of A and sends it to A bar tensor 1. And it doesn't matter which side of the tensor you put it, because one of the relations I had tells me that it's well defined. Okay, so this is a multiplicative norm. And so the next thing what we did, so we wanted to understand what's the real version of this theorem of Hesselholt and Madsen. So of course you have this O2 structure on real THH. This is actually a genuine let's say thin O2 spectrum. So it's, I only care about finite subgroup isotropy here. And so if you do that, then it's a genuine O2 spectrum. And so, of course, what you can do is you can ask yourself, take THR of it and take its dihedral dPn fixed points. So, of course, all of this is derived fixed points or diagonal fixed points, whatever I'm taking. And so now here's the next theorem, which we did recently. So, calculation of this thing in most of the cases. So the first part of it, it says that if you take phi 0 of this is indeed isomorphic to Wn plus 1 of the pi 0 of real THH. For P of. And as you can easily see, and you might know, the involutions business is somehow quite differently behaved with respect to odd primes and even primes. So, and for P is equal to 2, we have a partial result. If you take P is equal to 2.
So in this quotient, you quotient out the ideal and not the subgroup.
This is automatically ideal, actually. Yeah, so you can generate subgroup and then put it automatically in ideal. You see that. Right, so for P is equal to 2, what we have is the following. Assume from that. So assume that this map, I should look up if I need anything more in here. Right, so I need to know that this quotient, the multiplication from this quotient to the fixed points is injective. So assume that this map is injective. Then the same is true. So if you take pi 0 of the real THH of P2n, and this is isomorphic to W n plus 1. 2 tensor. And so the first case, which we cannot still cover, and I think we found a new method actually to tackle this question, but it's still very much under construction, is the case ZC2 with trivial involution. So we don't know this case. Yeah, so this is still open. And the reason is, of course, the way we prove this is trying to imitate what Hesselholt and Madsen did. And of course, things become complicated because you have to deal with Mackey functors instead of rigs, and at some point you have to look at some kind of Keller differential kind of thing for these kind of structures. But almost everything goes through, so there are certain exact sequences that you get, which we also get, but those sequences stop being exact once you put this. And then you have to basically come up with completely new technology. And I think we have an idea, but it's still under construction. So, but these two are definitely the things we did. And also you can ask some algebraic questions here, like obvious algebraic questions. So we know by theorem of Hesselholt and Madsen, let's say in this case, that pi 0 of THH of A CPN fixed points is isomorphic to detractors. So we know this, and we also know that pi 0 of the real THH DPN fixed points is isomorphic to plus 1 completed detractors of this quotient. And these two groups are of course related. Again, they together form a Mackey functor, and even more, they actually form a Tambara functor. And so we have this norm map here. And now the question is, what is this map here? And so there is an ad hoc way of defining this map, you can come up with some kind of sort of Witt polynomial style multiplication, which will actually describe this map for you. But of course, we wanted to understand more conceptually what this map really is. And so one thing we observed is that if you go to ghost maps, then it is indeed just applying this norm, which I described here, to every component of the ghost. And so this brought us to the idea that actually maybe we should study in general how these kind of maps behave with respect to these vectors. And it turned out that the story is actually quite nice. So there is a extra factoriality what these Witt vectors have with respect to these kind of maps, which I want to now describe. So this n here is something called two polynomial or quadratic map. And now I will talk about these polynomial maps. It turns out that in certain cases these Witt vectors have factoriality with respect to these kind of maps. So this is the topological way to arrive to this question. If you didn't like my motivation at the beginning, which is also, I think, a pretty good motivation to introduce all of these things.
Before you start, Hesselholt and Madsen,
Yes.
they didn't just talk about pi zero.
They definitely did way more computations, but this is one of the very first.
Yeah, so can you say, I mean, they had the whole round Witt complex going and everything.
Yeah, sure. I mean, there are many results in this direction. Like you can compute also pi one of these things, and then it's the Wn omega 1 always. So this is the first connection to the round Witt complex. And if you take a perfect FP algebra, for example, then you can look at the whole TR tower, and that actually turns out to be the round Witt complex. But then, I mean, then there are a lot of other sort of directions of this theorem. But this is actually the very first theorem they proved in the paper where Witt vectors show up with THH. Okay, so now I can switch to algebra again, and if you don't like THH, now you can forget about it basically, except that you won't understand how I solved this problem. So, okay, so now a definition, a map of, so F, and this is always a set valued map. Every time I say map, it always means set map, because I want to consider polynomial maps and not homomorphisms. A map of abelian groups, called a polynomial if the end cross effect of this thing, which is a multivariable function from a1 to an n, and now I should get this formula correct, otherwise I might get some complaints in the audience. So it's all the subsets from 1 to n, and the sign is minus 1 to n minus 1 to 2. Of course, the sign might be changed in your definition if you want. And f of all possible. Should have drawn this thing somewhere here. So this is L and U and L. And so what I'm asking is that this thing is n polynomial if this expression is 0. Okay, so what is this condition? I mean, I can only tell you the first two cases. Of course, n is equal to 0. This condition being a 0 polynomial is the same, just being a constant, as you can easily check yourself. And the second one, n is equal to 1, it's the same as affine linear. So that means a shift by a constant of a homomorphism. Because if you write out this condition, it's just fx plus y minus fx minus fy plus f0 is equal to 0. And that means that
Can you show
fx.
your conventions on, or for any equals 1 and those summing up?
Okay, I got it wrong again. Let's see. I have empty set. I have.
For n equals 1,
Yeah,
subsets
you're right.
of 1
So
elements that are
it
two and
should
not
be.
four, it's off by 1.
It should be n plus 1 first cross effect. I guess, right? Right, and then it's this.
We haven't changed anything now.
Okay, so let me think about it.
Yeah, but you know,
Keep the
formula and write n minus 1.
Okay, so I knew that this will pick up here. Unfortunately, I also don't have my notes with me, so let's see. Let's see, so, okay, so cross effect 0 should be just nothing but one term, which would be subsets of empty set, which is just empty set. So cross effect 1 should be, right, it should be fx minus f0. So that means I should write here n plus first cross effect. And n polynomial would mean that n plus first cross effect. And then I'm fine, because 0 polynomial would mean that the first cross effect vanishes. Actually, yeah, so, okay, minus 1 polynomial is just 0. Minus 1 polynomial is just constantly 0. Then the 0 polynomial is constant, and 1 polynomial is homomorphisms. Okay, and I guess then I should probably correct here the sign. Good. I think this is now right. We happy? So, yeah, and I cannot tell you anymore what happens in n is equal to 2. You can write out this expression, and then this is, and most likely I will make a mistake, so I'll try not to do that. Good, so, and what I'm really interested in today is, suppose we are given f, which is a polynomial, then what I'm really interested in is f is multiplicative polynomial map. So now suppose A and B are rings. Or commutative rings actually. So then f is multiplicative and polynomial map if just obviously hold, but I don't ask that units are preserved. You don't have to say that f1 is 1. Okay, so when I'm interested in multiplicative and polynomial maps, then just to give you right away examples of this thing. There are many examples. One of them is, for example, for any ring to the end map from A to A is multiplicative and polynomial. For example, the identity is one polynomial because the second cross effect vanishes. The other example is, for example, take a representation ring of a finite group H. I don't know, like the complex representation ring, and go to the bigger, which is a finite, and take the multiplicative norm here. So it's a representation, so it's multiplicative induction. So I don't specify now what's the action, but morally speaking, it's just as a product. Or you can do Burnside ring. And now some people already in the audience might ask me some question which I'll answer right away. So if you take your x, you can send it to also to the multiplicative norm. And in general, if you take any Tambara functor, consider map from TH to TG. These are all index polynomial. And so this is basically, I should give your credits to Strickland because this is written out in his big document about Tambara functors. So these are all index polynomial maps. Okay, so there are plenty of examples, as you see. So now, in particular, this norm that we have is a two polynomial map, and we see that there is some map on Witt vectors. So why don't we try to see if any map like this induces something on Witt vectors that has a reasonable behavior? And it turns out that the story is not as easy as you hope. So you need some kind of conditions which you need to impose to have this. And so here is the main result of this talk, which I want to discuss, and maybe I will leave this diagram here a bit in the corner to fill up at the end. Let me just keep this here in the corner till the end of the talk. So there's a theorem which we proved in this work that says the following: that suppose f to b is multiplicative and polynomial map, and assume that n is less than p for some prime p of x prime. So we fix a prime which is bigger than this number. So then there exists, then we construct, let's say like that, because there is an explicit construction, we construct a map called, let's say, WMF, where here m can be anything starting from 1 to infinity. So we have Wm of f from p typical m truncated Witt vectors of A to m truncated Witt vectors of B with following properties. The first one is that the obvious diagram goes commutes. So if you take ghost maps here from 0 to, and I was corrected, n minus 1 of course, to 0 to minus 1 of p. So this diagram commutes, where here you just take f of the those components, f of the i's. So in each, I mean, this is a stupid notation. Just take f in every factor. So this diagram commutes. That's the first condition, and the second condition is that if f is n polynomial, let's draw this from A to B f, and you take some other g which is g is k polynomial, and you know that the product is less than p, then this construction respects compositions. Same as the composing these two. And this uniquely characterizes these kind of maps. The condition that it commutes with goes and this holds uniquely characterizes those maps which have this kind of functoriality with respect to which the p-typical Witt vectors have this extra functoriality. So now there are a bunch of other conditions which are extra there, which are not needed anymore to show the uniqueness of these constructions. For example, if you take the induced map of the nth power, which I talked about up there, this is again nth power. One of the things you know. The other thing you know is that if you multiply two things, so this is say n polynomial, this is k polynomial, and n plus k is less than p, then this also respects multiplication.
It's n plus k less than p in condition 2 as well?
No, it's n times k because this was a composition. And composition has it's basically like in real analysis. Right, and the final condition is this condition here, n is less than p, is optimal. So I will give you now an example where this does not happen. There is no map like this which satisfies that. If n is equal to p, there are plenty of examples of that. Okay, so let me give you at least the construction of this map, and maybe this counterexample in 5. I will not prove, of course, all the conditions because they are pretty technical. use time to ask some questions if you don't understand anything in this formulation.
So n polynomial implies n plus 1 polynomial, right?
Sorry?
Does n polynomial,
Yes, yes, it does.
could simply have said p minus 1 polynomial and get rid of the n?
Yes, but sometimes you want to keep track of exactly which polynomial you are, because sometimes you just, you know, especially when it comes to these compositions, if I would say p minus 1 polynomial everywhere, I would compose them, and that will be not anymore p minus 1 polynomial, and then I would be in trouble. So I should rather keep track of, for this composition law, I should keep track of how polynomial am I in order to do this to make sense. If I would say, oh, it's just a factoring p minus 1 polynomial map, that's not even a category. That's the problem. You know, compositions are not reserved. You could say some partial functor, which is defined if the composition stays like that. It's another way to phrase this. I mean, that wouldn't be a problem to do that. Okay. Right. So let's prove this. At least give a construction. But before I prove this, maybe I should right away give you an example of this 5. So let's take the case n is equal to p. So consider a norm from the cyclic group of order p. So go from Z to the Verside ring of Cp, which is polynomial algebra modulo 1 relation that x squared is x squared minus dx. So this is a p polynomial map. As one can easily see, if you go to 2 truncated p-typical Witt vectors, so now it's important that this is exactly p-typical Witt vectors, otherwise this would be uninteresting. So on 2 typical Witt vectors, you can try to find a map. So you might ask yourself, does there exist anything like this, which will have a property that on the ghost maps is true? I mean, there is even an explicit formula for this norm you can write down. Maybe I should not do this because of time. But very elementary check with congruences actually tells you that such a thing never exists. You cannot define a map such that this will ever commute. So this shows you that actually this condition that is less than p is very important. So I want to right away comment also about the beginning of the talk. So when I had the composition of degree 2 and degree 3 and degree 2 and degree 2. So the first case was not okay and the second case was okay. Reason is exactly this condition that when you compose things, you should better stay in your degree less than p, otherwise, yeah.
I think I missed it, like you're saying, I don't know, maybe the condition is that n does not divide p, or p does not divide n?
Where?
I don't know, you said n that has to be less than p?
Here, yeah. I mean, this is exactly what I'm showing. There is no map like.
Sorry.
No, the index on the W can be anything from 1 to infinity.
Oh, I see, okay.
Yeah.
Thanks.
Yeah. Yeah, so here, yeah, here, you mean, yeah, this can be anything, yeah, right. Yeah.
So there must be an element in the, if I wanted to do this at home and get some help from you, there's some element in the lower left corner which comes from upstairs, but if you go across it doesn't come from upstairs. So what's the element in the lower left corner? 2 integers.
Yeah, I don't remember anymore, but there is one. I think it's, yeah, I'll tell you after the talk. I mean, the thing is that there is this Frobenius acting on this thing, and you can always easily check if something is in the image of this kind of ghost. You can do this by hand, or there is something called Dwork's lemma, which basically controls when the things are in the image. Okay, right. Okay, so now the next thing I want to say is the proof. So what you can do is you can right, so going back to this example at the beginning of the talk, so I composed the degree 2 map and degree 3 map, and this was a degree 6 map, and so it didn't stay less than p, so therefore the functoriality kind of failed. It didn't really capture the thing. But in the case of degree 2 and degree 2, it was degree 4 eventually, and so it was p was 5 in my example, and so therefore it was fine. So this is basically the explanation I was promising. Okay, so now proof is as follows. So first of all, p-typical Witt vectors only depends on the p-localization. I don't want to go into details of this, but if you write down those components, they only include the number p in it, and so it's very easy to see that mapping into Witt vectors is the same as mapping into p-typical Witt vectors of p-localization. So in order to define a map for you from W and A,
What's the precise meaning?
the precise meaning, this was this thing 3 days ago I was talking about, and you guys were all making fun of me, so the statement is that if you take p-typical Witt vectors, so you map it into p-localization, then you can look at the ghost components, and also here, and this is a pullback. I don't know, this is the
Yeah, criterion. Criterion.
This was the great criterion I came up with 2 days ago, and all making fun of me. So this is correct, and therefore, in order to map into this, and in order to define W and F, you can just equally assume that you do this for localization, because you already are prescribed what you should be by the condition, by the first condition on ghost components. So I should rather just tell you how I define this map, and then compatibility will be obvious. I will also define a map into W and of B. So in other words, without loss of generality, I assume that this is local.
Slightly confused. This is some hidden assumption on B. You know,
No,
if P localization kills B, then the right things are both 0, but
No.
the left is not an isomorphic.
I didn't. P-localization for me means inverting everything except P.
Yeah, but
I
if
never
that
killed
kills
it.
the ring, for example, if it makes the ring 0, then on the right hand side you have 0 rings everywhere, but on the left you don't have an isomorphism. The ghost
I mean, so are you taking, say, FP or something?
take FQ or FL.
Yeah, but then it's not a problem. Then ghost components are isomorphism in that case. P-typical
they
Witt
are.
vectors, and
Oh,
you already know everything.
I see.
That's the point. But yeah, what I'm saying is that I have here already something prescribed. I know what I want to do here is all the ghost components, from W and M. I know what I want here, and if I construct something here so the thing is compatible, then I can also construct it here. That's what I'm saying. So in other words, I will assume that this is P-local. So now if F is an N polynomial map, then all the 1 over K factorials live inside B. B is P-local for K less than P. And this is why this condition N is less than P showing up, which I'm asking at the beginning already. So now if you have this, then you can do some real analysis. That's what I was talking about. So F0 plus F1 and so on and N. So you can do the Taylor expansion. This F into Fi being I polynomial homogeneous maps. Do a Taylor expansion of this F. And now what I will do first, I will define for you what is Wm Fi, Wm of A into Wm of B. And so this is a bit technical. So if you have an N polynomial map like this, so I polynomial map like this, which is also homogeneous, so I polynomial homogeneous, then this always factors over the ith graded piece of divided power algebra. So there is something called Fi bar. So what is this gamma I? So you can take A as an abelian group, and you can take divided power algebra on this. And this has the ith graded piece, which is exactly products of ith divided power, so that sum is exactly k divided power, so the sum is I. So now the thing is that if A and B are rings, if A is a ring, then this particular thing is also a ring. So this has nothing to do with the ring structure the divided power algebra has. This is something similar to symmetric tensors of a ring have a ring structure, because it's the fixed points of A tensor N, which is itself a ring. And so the same kind of ring structure exists here. I mean, we didn't invent this. This is 60s and 70s literature. And if F is an I polynomial homogeneous map, which is additionally also multiplicative, and if you start it here with a multiplicative map, then the Taylor expansion is also multiplicative every single step. It's even orthogonal decomposition if you are worried about that. And so such a thing always gives you a ring map like that. So this will be a ring homomorphism. I'm ignoring here the issues like that this will a priori not be unital, but Witt vectors are also functorial in non-unital ring homomorphisms, so I'm not worried about that. Okay, so now we are ready to define this map. So we can start with p-typical Witt vectors of A, and we can go with the usual divided I power map to I divided power of A. W map. So now there is a canonical map always from here to Wn gamma I of A. And so this is a slightly non-trivial observation. So Witt vectors is a symmetric monoidal functor with respect to tensor product of commutative rings for obvious reasons, like symmetric monoidal because it's a coproduct and every coproduct. I want to commute coproduct map always exists, but it's not an isomorphism. So in particular, then it has this kind of map, comparison map for symmetric tensors. So now for torsion-free A, both sides are torsion-free, and therefore these are actually symmetric tensors. But when A is a torsion, then you have to do some kind of extension argument, because both these functors actually commute with Sept colimits. And if you say it what it does on torsion-free things, then you can descend it via standard resolution or something like that. So there is always a natural transformation like this. But now I can use this Fi bar, which is ring homomorphism, and define something like this. Compose it like that, and this is my definition of Wm of Fi. And so in general, Wm of F will be the sum of these things. So Wm of general F, whose Taylor expansion I took, will be just the sum of Wm and Phi, where this just means literally pointwise sum of functions. And so this is the construction we are doing. Of course, I will not check now all the properties, but one thing I want to say is that first solve this problem in, say quickly what this thing does in topology. So one thing I should notice is that these kind of maps which factor over divided powers are called polynomial laws. And actually what we are really doing in this paper, showing that these Witt vectors are factorial with respect to polynomial laws, and first actually studying these kind of maps. So I'm sweeping this under the rug here a bit, and I don't want to go into details. But the thing is that it turns out even that this norm, which I was talking about in the case of real THH, it's actually W of Wn plus 1 of this n, where n was now the norm inside the real THH, so going from A into this thing. And now this is a special case of this construction. But actually it turns out that you don't really need this constraint p is bigger than n in this case, because this thing is already a polynomial law. It already factors over this divided power, because it's some kind of a special example. Already has this factorization over divided power, and I only needed these constraints in order to factor it over divided powers, which a priori is not clear. But in this particular case, it already has this factorization over divided powers, because any two polynomial homogeneous map is already a polynomial law. It already factors over divided powers, because gamma 2 is so simple. But in general, of course, this is not the case. So this is somehow a baby application of topology of this theory. You don't have to develop all this theory, in other words, to actually compute this map. But I think it gives it more conceptual sort of understanding if you compute it like that. Okay, so now I have an elementary application in algebra of these results, and of course we hope to find more applications of this thing in algebra and in topology. So if you have any ideas about some of these maps, where they might show up, please let me know. So I want to comment on two things though before I give you this example. One is there is this work by Warwick, Glassman, Matthew and Nicolaus about polynomials, functors, and K-theory, where they show that K-theory is, algebraic K-theory is factorial in polynomials functors. Unfortunately, this thing is not related to that, or morally it is related, but unfortunately we tried hard in Bonn, and we also consulted with some very smart people, and we couldn't really figure this out. So it turns out that if you have such a polynomial map, it doesn't give you a polynomial functor in general. And the thing is related to the fact that these divided powers are badly behaved with respect to perfect complexes. If you start with a perfect complex over some ring, and you apply divided powers to both of them, so the ring and the complex. doesn't stay perfect, so the projectiveness is violated. And so therefore you cannot expect that some kind of polynomial laws like this to give you the kind of setup what these four authors are doing. So the other work is the work by Angeltweit, where he studies norms and Witt vectors. That's some kind of orthogonal direction to what we are doing, because he's studying natural transformations which are natural in ring homomorphisms, whereas this is sort of completely focused on sort of P and polynomial maps like functoriality and polynomial maps. Just that you are aware of if you have seen these examples before. I actually started 3 minutes later. So if you are looking at the clock and you are thinking about, I hope this guy will be done in 2 minutes. No, I will not be done in 2 minutes. I will be done in 5 minutes. So let me show you the example. So example. Everything is related to the fact that you came here late. So no matter. Enjoying your coffee and tea. I was standing here waiting for you. So okay, so so okay, now the example I want to take is I want to show you how to apply this composition law which I deleted. So I was telling you that this induced map of Witt vectors is satisfying this, but only if this was k polynomial, this was n polynomial, and k times n was less than p. Otherwise, that we get in trouble, and you could see that in the beginning of the lecture. But now, where can you apply something like this? So what's the elementary application, for example? So you can try to take, for example, subgroups of a group which are maximal but which have a non-prime index. For example, A3 inside A4 is, I think, the smallest example I know where you have a subgroup which is maximal but whose index is 4 and not something prime. Cardinality, and so now you can look at the norm. Sorry?
Sorry.
So we have a map from the Berside ring from A3 to A4, which is a norm from A3 to A4. And so this is, as we said before, a full polynomial map. And now you can ask, does there exist a factorization of this thing into two maps, where this is 2 polynomial, this is also 2 polynomial. And so if you try to solve this problem from scratch, have fun, because I mean this map is pretty complicated. Even writing down the closed formula what this thing really is a bit hard. So if you would have a subgroup which is not maximal, and you have some smaller subgroup in it, you can always factor this norm map into composition of smaller polynomial things. What I'm claiming now here that this does not exist. So you cannot factor this map into a composition of two polynomial maps. And reason is, if you look at two truncated three typical Witt vectors, and 3 is a number that sits exactly between 4 times 4 and 2. So there does not, sorry, 2 times 2. That's the important thing. So there does not exist a map W2 from A3, sorry?
What's the Witt vectors 2 and then the comma?
This is 3 typical, I just want to emphasize this is 3 typical, but now I will drop this notation, okay? So already on 2 typical Witt vectors, you can see that there does not exist a map like that.
There's still 3 typical, right?
They are still 3 typical, so Witt vectors now became 3 typical. Prime
You
is,
just said 2 typical.
alright, yeah. Prime, P is 3, right, good point. So if you want to try to find such a map such that the corresponding ghosts behave as you want, you will not be able to do this. And this is a bit of a complicated calculation. You have to really write down these things. So does not exist such a thing where this would be commutative. And reason for this, if you really unfold everything, is that you compute at some point norm of 4, then it turns out to be 1 plus 14 times a 4 modulo trivial thing, where this is everything modulo 3, and 3 does not divide 14, so that will make you believe that actually this kind of thing cannot exist. So now, as you might guess, all these kind of things you check that these kind of things do not exist are some very brutal congruences which you have to like write out and things like that, but it just turns out that the Witt factors package these congruences in such a way that you can formulate this condition in terms of induced maps in Witt factors. And this is why Witt factor kind of things are around to sort of package these kind of congruences together. And so from this principle now you can see that in general if you have K polynomial map, N polynomial map, and you have a prime that sits between K times N, K and N, you can always ask, does this kind of Kn times polynomial map factor as a composition of K polynomial and N polynomial map? And using this example, you can see that you can actually use p-typical Witt vectors to detect if this does not exist. So if you want to prove that Kn times polynomial map does not factor as a composition of K and N polynomial maps, you look at Witt vectors of this map, induced map on Witt vectors, and you can see if this thing even exists, satisfying this kind of condition. If it doesn't, then you know that it doesn't factor. So this is the example. I did say this a bit in a confusing way, I guess, because people seem to be very confused. But I think I'm done. Thanks.
Does this polynomial stuff tell you that you can put some kind of congruence information on the polynomial map so that you can get a lift?
Yes, exactly. This is exactly what it is. So if you extend it to n polynomial law, this tells you actually that like in this setting when n is less than p, and actually why is this happening that you can extend it to the n polynomial law is that these things actually satisfy certain congruences. Like if you take f of x plus p to the k something, then it behaves in a certain way with respect to these kind of expressions, which are some kind of huge binomial coefficients, of course. But yeah, you can control this kind of congruences. Yeah.
Fabian and I have missed the point. So why can you use free typical to make this contradiction argument? I mean, it's
Because
not supposed to be functorial after when the product is larger than 3. So I mean, you're not supposed to have an induced map in 3 typical Witt vectors because it's a degree 4. So why does this? Why is this a contradiction?
Wait.
I'm larger than the product.
Yeah, if you lose the prime larger than 4, then.
Yeah. So, wait. Okay, just some point here. Wait a second. So, no, the thing is, yeah, that's the point. The point is that K and N are less than P, so K polynomial map will induce something on P-typical.
Yeah. So you would have the 2 induced maps, but
Yeah.
why do you
So, but then these two both satisfy this thing with respect to ghosts. If you go to ghosts, you can compute their ghosts. So altogether in the composition of ghosts, you will get this. That's the point.
That was the point. Okay.
But you are confusing me
Thank
now
you.
here. But I got you. But I got confused
You were
on
also
this one.
confused by your own arguments. Okay, I got you now.
Yeah, so that's the, thanks for the question, because I think this is what I wanted to say in a more complicated way before. Yeah.
Even worse than, like, sillier than the previous question. When you talk about non-unital maps, multiplicative maps, are you
Yeah.
just including 0 maps?
I do include the 0.
But
So when I talk
other
about,
maps aren't there also?
so yes, so when it comes to these constant maps, I mean, this was kind of a bit of an issue also at the beginning for us before we worked out theory. So when it comes to multiplicative polynomial maps of degree 0, these are idempotents. So basically these are idempotents. In particular 0 is allowed. This is a multiplicative polynomial. But any idempotent is also a multiplicative 0 polynomial. Yeah. And so for those, anything what I was talking about, like topologically goes through.
Any minutes?